Hello friends, today I am now going to discuss about Kepler's second law and third law. In my previous classical mechanics video, I have discussed about Kepler's first law. Today I am now going to discuss Kepler's second law and third law. So let's start the discussion. So what about second law? First of all, Kepler's second law. What is that? So Kepler's second law is that in our previous video I have shown you the figure. I'm again showing you that figure, that drawing. So in our previous video we have shown this figure. Here it is r is the radius vector and it is r plus dr, and this portion is r d theta. This is d theta because we have discussed also that s equals r theta. So what we have discussed that in case of that aerial velocity will be constant. Aerial velocity we got half r square theta dot etc etc. We have discussed. Now what is a Kepler's second law? According to that law, radius vector drawn from sun to planet. Let us consider sun here, and here it is planet. Sun to planet sweeps out equals area in equals time. That is, aerial vector is constant in case of planetary motion. That is, if I draw an radius vector, Kepler's second law of planetary motion actually states that if I draw radius vector from sun, here it is S, to planet, so these will sweeps out equal areas in equal time. That is, aerial velocity. We have discussed that what is aerial velocity in our previous video of classical mechanics, half r square theta dot. It is aerial velocity. I have shown that from that figure, half r square d theta by d theta by dt will be constant for planetary motion. Will be constant for planetary motion. We have discussed about that these things, half r square theta dot, how it is coming. So this is the Kepler's second law, which is actually stating that for planetary motion, if the radius vector sweeps out, radius vector is such that it is drawn from sun to planet, it will sweep equal area in equal time. So I'm showing you by mathematical expression, otherwise you will not understand. So mathematical expression is, let us consider dA by dt. That is, A is what? A is means area, dt means area rate of change of area. That is J by dt, half r square theta dot aerial velocity equals J by 2m. J equals, we have got first integral of motion m r square theta dot. We have already got that half m r square theta dot. So dA by dt equals half r square theta dot equals J by 2m. This term will be constant. This is the Kepler's second law. Nothing is too much difficult in this case. Actually, this law is same. Gravitational force is a central force, and this law is same. And this statement is given by conservation of angular momentum in central force field. So we have got, this is the mathematical expression of Kepler's second law. Now, deduction of Kepler's third law. Kepler's third law of planetary motion. Okay, what is actually Kepler's third law? Kepler's third law actually states about period of motion in an elliptical orbit. Yeah, in an elliptical orbit. So it is an actually statement, but what is actually that? So for this thing, I have to draw an elliptical orbit. For that, let us draw that thing. So here I have drawn an elliptical orbit. Here this is the semi-major axis. I'm not changing the pen color, then you can understand. So this is the A is in semi-major axis, and B is semi-minor axis. You can understand from here. And here it is a sun S, and here it is a planet is moving, and here it is R radius vector. This short thing is R1, and this thing is R2. Okay. So now we'll deduct Kepler's third law of planetary motion. So we have got an equation, from our previous video of Kepler's first law. What was that? We got, let me change the pen color again, because yellow is much more visible than red. L by R equals 1 plus E cos of theta minus theta prime. We have got that. And for elliptical orbit, what is the condition we have got? E less than 1, E less than 0. For elliptical orbit, we have got some condition that if E equals 1 plus root 2E j square by mk square, then E greater than 1, that will define what? That will define E greater than 0, that will define hyperbola. We have got another condition that E equals 1. E equals 1 means what? E equals 1, that will define E capital E equals, that means energy is 0. E eccentricity is 1, energy is 0, and that will define a parabola. And we have got what? I'm just recapitulating that portion to you. E less than 1, we have got E less than 0, and that case we have got ellipse. Another case we have got also for circle, small e equals 0, and E equals minus mk square by 2j square, that's it. So I'm again writing that property. L by R equals 1 plus E into cos theta minus theta prime. We have got this. And we have got this thing also, that E less than 1, E and energy less than 0. This is for elliptical. Now L equals what here? L equals what? J square by mk. And E equals root, L equals, we have got j square by mk. And small e equals, we have got 1 plus root 2e j square by mk square. We have got this also. Now I'm again returning to that equation, L by R 1 plus E cos of theta minus theta prime. So now when theta minus theta prime equals 0, what we will get? We will get this thing 0 means cos of 0, that means 1. This will give what? This will give 1. Now cos of theta minus theta prime equals 1. Then what is the main thing is coming? Cos of theta minus theta prime equals 1 means what? L by R equals 1 plus E. We are getting cos of theta minus theta prime is 1. That means what? That means the value of R at R equals R1 is minimum for theta minus theta 1 equals 0. Why? Because see here, L by R 1 plus E cos of theta minus theta prime. So theta if is 0, then R equals what? L by R equals 1 plus E, and R equals what? L by 1 plus E. And when we are same thing, when we are putting theta minus theta prime, we are putting theta minus theta prime equals pi. When we are putting theta minus theta prime equals pi. Now cos pi what? Cos pi minus 1, then L by R equals what? L by R equals 1 minus E. That means what? That means R equals what we got? That means R equals, we are getting L by 1 minus E. In that, and R equals for theta equals 0, what we have got? L by 1 plus E. So this is minimum, na? Because denominator it is maximum thing. So radius R equals R1 is minimum for theta minus theta equals 0. And this is maximum. This is maximum for theta equals pi. Yeah. So for theta equals 0, we are getting minimum L by R1 equals 1 plus E. So we are getting R1 equals L by 1 plus E. So we are getting minimum. and this minimum position is known as what? I am giving that name L by 1 plus E equals R. This minimum position is known as perihelion. And when we got L by R2 equals 1 minus E, so R2 equals L by 1 minus E, this thing is known as aphelion, this position. So we have got two things. So conclusion is what? We are getting two things. For theta minus theta prime equals 0, we are getting R equals L by 1 plus E, and that is perihelion. It is minimum radius. And theta minus theta prime equals pi, we are getting what? L by 1 minus C, that is maximum, and that is what? That is aphelion. So we are getting another thing, semi-major axis also. Now we have got that A equals R1 plus R2 by 2. Why? Because we have got A equals semi-major axis. A equals semi-major axis. I'm again showing you that picture, then you will be cleared. Such as if you have drawn an ellipse here, I'm bisecting it. So if this is semi-major axis A, and here sun to planet, S to P, sun to planet is here. This portion is R1 and this portion is R2. So R1 plus R2 equals this total portion, but A is what portion? That half of this total portion. So we can easily write that A equals R1 plus R2 by 2. Now R1 equals what we have got? R1 is R minimum. Therefore theta minus theta prime equals 1 by E. And R2 is R maximum, that theta minus theta prime equals pi, so cos pi minus 1. So L by 1 minus E. So R A equals, we are getting, let me write properly here. A equals, we are getting here half of L by 1 plus C plus L by 1 minus C. So we can write lastly L by 1 minus E square. A equals, we are getting L by 1 minus E square. Now E equals what? E equals 1 plus root over 2E J square by MK square. So E square equals what? 1 plus 2E J square by MK square. So 1 minus E square equals what? 1 minus E square equals 1 minus 2E J square by MK square. So only we are getting 1 minus E square equals minus of 2E J square by MK square. So we are getting A equals, we have got A equals what? We have got A equals L by 1 minus E square. And L equals what? J square by MK divided by 1 minus E square. 1 minus E square we have got. So I'm writing here 1 minus E square we have got, minus of 2E J square by MK square. So A equals minus of J square by MK into MK square, 2E J square, minus of 2E J square by MK square, and that will be upper side denominator, and denominator and numerator will be inversed here, because if you write here minus of 2E J square by MK square, that will be that will go to the upper position, and here it will be MK square into by 2E J square. Here E is, capital E is energy. So here j square will be cancelled out, m will be cancelled out, k and k square cancelling out and will give k, and only 2e is remaining here. So we are getting a equals minus of k by 2e. We are getting k equals of a equals minus of k by 2e, or energy what we will get, energy we will get minus of k by 2a. It's very important, very important thing is it is that. So what we can conclude from here, we are getting E equals minus of k by 2a. A is what here? A is semi major axis. So, and what case we have taken? We have taken E less than 1 or E less than 0. That means elliptical orbit. So in case of elliptical orbit, total energy depends only on major axis. Depends only on major axis. That is the thing. Thus, in case of an elliptical orbit, total energy depends solely on major axis. Now, we will proceed to Kepler's third law. If t is periodic in time, t be the periodic in time, with in which particular radius vector completes one revolution. That is, t is the time in which particle will complete a particle, or you can say radius vector. Radius vector will complete one revolution. Then the area of the orbit complete revolution, one revolution. Then the area of the orbit can be we can obtain here. Area of the orbit will be here a equals 0 to a dA. Firstly, what we are trying to prove here, we are trying to prove we are trying to derive Kepler's third law. So, and Kepler's second law, we have what we have got? We have got that radial velocity is constant in planetary motion. That is, radius vector from sun to planet will sweep equal area in equal time. So, area is integration 0 to a dA, and from now here it is coming the Kepler's second law of motion. From Kepler's second law of motion, we have got what? dA by dt equals half r square theta dot. So dA equals what? dA equals, we have got half r square theta dot into dt, or equals, we have got what? We have got that j by 2m also. So we can write here, in case of now a equals integration 0 to a dA, and if we write it in terms of time, we can write 0 to t half of r square theta dot into dt, half of r square theta dot into dt. Now we can write here equals 0 to capital T here, integration j by 2m from the Kepler's second law into dt, or we can write jt by 2m, jt by 2m, that is the area. So t is what? T is, we are getting t equals 2m into capital A by j. Now area of ellipse is what? Area of ellipse is pi AB. Pi AB. So we are getting time period is equal 2 pi AB m by j. Area of ellipse we are getting 2 pi AB m by j. Now you have to know the property of ellipse. Property of ellipse is what? Relation between semi minor axis and major axis. B equals a into 1 minus e square. It is semi minor axis and a is semi major axis. So from here we can write 1 minus e square. What we have got? 1 minus e square we have got from A. A equals, we have got L by 1 minus E square. Just before, few times ago, we have derived this. A equals what we have got, L by 1 minus E square, and B equals what we are getting. B equals, we know, 1 A into 1 minus E square. So we can write here root over 1 minus E square equals root over L by A. Yeah, root over L by A. So B equals what we are getting. B equals A into 1 minus E square equals A into root over L by A. L equals what we know, J square by MK. L equals J square by MK. Then we can write J square by MK into A. L equals J square by MK into A. So now finally we can write what? We can write B equals A to the power half J by root MK. B equals A to the power half J by root MK. And A equals, we have all what we have got L by 1 minus E square. A equals L by 1 minus E square, and B equals what we are getting, A to the power half J by root MK. So L equals, again we can write what? We can write another term also. We can write A equals L by 1 minus E square. L equals J square by MK. So J square by MK into 1 minus E square. So 1 minus E square, what we can write? We can write 1 minus E square equals J square by MK. Another equation. We are getting so many equations from here. What an equation we have get 1 minus E square equals J square by MK. And in terms of B, what we have got? In terms of B, we have got A to the power half J by root MK. Now we'll put this A and B in the T. T equals 2 pi AM. We will now get T equals 2 pi AB M by J. Now we will put that A and B. What we have got A equals, we have got in terms of J square by MK into 1 minus E square, and B equals, we have got A to the power half J by root MK. So that thing if we put here, we will get A and B. If we put A and B, we will get T equals 2 pi A to the power 3 by 2 root M by K. This gives what? That means we are getting what? T equals 2 pi A to the power 3 by 2 root M by K. This gives periodic time in elliptical orbit. Or we can write T proportional to A to the power 3 by 2. If we square it, we can write, so we can write T proportional to A to the power 3 by 2, or we can write T square it, T square proportional to A to the power A cube. This is the Kepler's third law. What is that? So it states what? This T square proportional to A cube, it is the Kepler's third law. It states that square of period of revolution around the sun is proportional to the semi-major axis cube of semi-major axis in case of elliptical orbit. A is what? T is the square of period. T square is the square of period of revolution. T square is what? T square is square of period of revolution of a planet around the sun is proportional to the cube of semi-major axis of elliptical orbit. So this is actually the formula for Kepler's third law. So that is it for today. Thank you.